Good morning, everybody. So we're going to continue the discussion on lattices, on crystals. So let me remind you briefly the definitions that we introduced on Wednesday. We talked about the Bravais lattice. Bravais lattice is simply the array of points located at multiple integers of the primitive vectors. And then we've introduced a crystal structure or Bravais lattice, or lattice with a basis, which consists of a Bravais lattice plus additional points, a finite number of additional points, which need to be translated according to an underlying Bravais lattice. Okay, so these are the two definitions that we've introduced last time. And then we discussed some examples of Bravais lattices in 3 dimensions, in 2 dimensions and in 3 dimensions. And I'd like now to discuss a few examples, additional examples of Bravais lattices in 3 dimensions, in addition to the ones that we discussed last time. In fact, the ones we're going to discuss today are probably the most common examples of Bravais lattices in 3 dimensions. So what we're doing now is to discuss Bravais lattices in 3 dimensions. It's sort of continued. Okay, so we continue the discussion we started last time about Bravais lattices in 3 dimensions. Last time we discussed the cubic lattice, the tetragonal, orthorhombic, hexagonal, triclinic, monoclinic, and all that. Now we're going to discuss a different class of Bravais lattices, but of course they're quite common. Actually, they are the most common Bravais lattices in nature. One of them is the one that that describes the crystal structure of aluminum, for example, which is the FCC. So let me start with the first one. The first one is the body center cubic lattice. Or BCC for short. The BCC lattice is characterized by this following structure. So we have a square lattice. So always think in terms of this extending, of course, from minus infinity to plus infinity, right? So we place the origin here, and we have points located here, 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 as well as, of course, along the continuations of this and so on and so forth, right? You always have to consider this as an extended system, an infinite system. Okay, it's supposed to be cubic, whatever. Okay, so we're talking about a cubic lattice to start with, but we're adding an additional point, and we place it in the middle of the cube. So you have to now use your imagination to see this. So this point here is going to be located exactly in the center of the cube. And if there is one here, there has to be also another one here. And another one in all the cubes that we are building to construct our infinite crystal. Okay, so this is not a cubic lattice, or at least it's not a simple cubic lattice, because the simple cubic lattice would be composed of only the points that I draw initially. But there is an additional point at the center of the cube. And this lattice is called the body center cubic lattice. Now, of course, the question is this a Bravais lattice or not? Right? Even the honeycomb lattice, if you remember, was a simple lattice, was nice to, it was clearly a lattice, and it was actually composed, as it turned out after our discussion, it was composed of a triangular lattice with a basis of 2 points. Now, it is quite clear that this lattice here can be described with a simple cubic lattice with the basis of 2 points, this one and this one. Right? I just need to take a simple cubic lattice and say, and now I'm adding to the simple cubic lattice a basis, which is composed of the point that was originally in the Bravais lattice and another point in the middle of the cube. So it is obvious that I could describe this BCC lattice as a simple cubic lattice with a basis of 2 points, 2 vectors. One being this one here, one, and the other one being this one. Okay, so I can say that this is, there's no, I mean, I'm saying nothing wrong when I say that the body center cubic lattice is a crystal in the sense that we discussed last time. It's a crystal structure. And it is composed of, let me call it now simple cubic structure plus 2 vectors, B1 and B2. I'm not going to draw them now, but it's 2 vectors, B1 and B2. So it's a lattice with a basis. Nothing wrong with that. The question now is, however, can I describe this crystal structure as a Bravais lattice? Can I express all the points that I'm generating in this way also as a Bravais lattice? That is, can I find some primitive vectors that allow me to express all these points just using integer times some 3 primitive vectors? Yes?
Previously we said that the Bravais lattice, when we are introducing lattice with a basis,
Yes.
that the Bravais lattice is there and it is lying, okay, it is underlying this.
Yes.
And when I look at that, it is only that middle point that we are adding onto the Bravais lattice of the simple cubic.
Yes.
So I would think that our basis here is supposed to be the point for the one in the center.
Yes, okay. So your question is, if I understand it correctly, is that when we've introduced crystal structures, we introduced it with a Bravais lattice plus additional points in the basis. And your question is, we only need to add 1 point. Is that the question? Okay. Then you might remember yesterday that when we introduced the additional basis, the basis vectors, the 2 vectors or the 1 vector of the 2 vectors, if we want this point to belong to the lattice, we need to explicitly say it, right? So in this particular case, B1 will be just 0. In other words, a Bravais lattice is a crystal structure with just 1 element in the basis, and this element is 0. All right? So we need to include it explicitly. Okay? So again, a Bravais lattice is a particular case of a crystal structure in which we only have 1 element in the basis, and that element we can place it at the origin, 0. So now we have clearly we have 2 points in each, for each point of the Bravais lattice, of the simple cubic Bravais lattice, okay? So now I need to be a bit more specific. So with the green vector here, I'm identifying the primitive vectors of that define the simple cubic lattice. This one. Okay? So the green vectors are the primitive vectors of the simple cubic lattice that generates this crystal structure, on top of which I'm adding the 2 vectors, the two elements in the basis. B1 being this one, and B2 being this vector here. And B1 is just 0, because this is at the origin. All right? So a body-centered cubic lattice is a crystal structure composed of a simple cubic Bravais lattice, the one generated by the green vectors, plus 2 elements in the basis, one being the origin and the other being the point at 2, B2. Now, let me come back to the question. Can I simplify my life and describe the same lattice in a different way, in a simpler way? That is, is it a Bravais lattice? Is this lattice here a Bravais lattice or not? It is, right? But in order for me to show that it is, I need to find out the primitive vectors. I need to find some primitive vectors that describe this Bravais lattice. So I'm now going to use the pink color to show you what the primitive vectors are. The first one is the same. Oh, let me call it, let me put a prime to identify the new primitive vectors. A3, I leave it the same. And I call it prime. But then I use B2 to identify the second one. Okay? So in other words, what I'm saying is that this is equal to a Bravais lattice with primitive vectors A1 prime, A2 prime, A3 prime. And that's it, Bravais lattice, so I don't need to introduce an additional point. Is it true, by the way? Well, with A1 and A3 prime, I will cover the whole sort of ground floor of the structure. With A2 prime, I'm going up half a floor, right, with respect to the cubic structure. But then I can move with A1 and A3 to reach all the points that are at the center of the cubes in this first floor. And then I can go up again with A2 prime, and I end up here at the opposite corner of the first cube, right? If I continue twice A2 prime, I will end up here. So I climb the full floor. And now I can move with A1 and A3 and I cover the full floor there. Okay? So this is correct. This is a correct statement. Now, this is a bit surprising in some sense because we've introduced this concept here of crystal structure because we were unable to describe some structures. You remember the honeycomb lattice was the example we used last time. We had the honeycomb lattice, we have a structured lattice that we were unable to express using the Bravais lattice concept. Now we have somehow the opposite problem. We have a problem that we have something that can be easily described with a crystal structure. However, it can also be described by a Bravais lattice. Of course, there is a difference in the two approaches. In this approach here, the primitive vectors are just the edges of a cube. So they're very simple to visualize. Also, in some sense, in this approach, we fully preserve the symmetry of the problem because this is still a cubic system. So whether I consider it rotating by 90 degrees or 180 degrees, it doesn't change, right? So if I use this approach here, everything becomes quite clear. These primitive vectors are clearly along the Cartesian directions, and say my life is going to be much easier if I use this to describe my system. Vice versa, if I use this approach, of course, on one hand, I'm simplifying my life because I'm reducing the complexity to a Bravais lattice, which is very simple with respect to a crystal structure. On the other hand, I have to break the symmetry because I have to choose A1 and A3 and then A2 to climb up the floors. But I could have done it also in the other way. I could have chosen A3 and A2 and climb up with A1 or with, again, B2. So you see that somehow I've lost some information about the symmetry of the problem by doing that. Okay? And therefore, I mean, this is an example in which it is typically preferable to stick to this description rather than to try and simplify your life further and try to describe with a Bravais lattice. Yes?
Would it be sufficient if I expressed that the extra point that you have added in the center, express it in terms of the former primitive vectors?
Okay, so you're asking whether I can express the center, the point here, B2, in terms of the primitive vectors, but which ones? You mean the green ones?
Yes, the green ones.
Oh, okay, well, there's no way you can express, of course, this one in terms of integer times these vectors. right? Because this is exactly in the middle of the cube, so you would have to express it as 1/2 A1, 1/2 A2 plus 1/2 A3. If you wanted to describe B2 as a linear combination of the green primitive vectors, you could do it, but it would be, the factors here would be 1/2, right? B2 is equal to 1/2 A1 plus A2 plus A3, right? So this is not an integer. So you could do it, of course, but there's no, I mean, you wouldn't gain anything. It would just be one way in which you could express B2. But you wouldn't gain anything in terms of, say, showing that this is a Bravais lattice, because this point is not an integer times. So you wouldn't be able to incorporate it here as a Bravais lattice point because this is not an integer. There is an obvious example in 2 dimensions also that where you can easily understand this concept. And let me just flash it here on the right. Suppose you have this lattice here, a lattice which looks like a square lattice, but you add a point in the middle, right? This is also a lattice, right? It's clearly regular, clearly. Now you can obviously describe this lattice using A1, A2, and B2. Of course, B1 being this vector here. Therefore, as a lattice with a basis. But it is quite clear that you can also do this, right? If you now see it this way, well, then you immediately realize that this is also a Bravais lattice, right? You just need to define this as your primitive vectors. And this is a simple square Bravais lattice. So you have 2 ways in which you can express the same lattice, either as a crystal, that is, as a crystal structure, that is, as a Bravais lattice with an additional basis of 2 points, or you can describe it by a single Bravais lattice, choosing, of course, a different choice of the primitive vectors. So this is just to say that sometimes, even in the literature, there may be some ambiguities. If you read a paper, you must be careful that when they talk about BCC and they give you some primitive vectors, you have to be sure that which kind of convention they're using. Are they using this convention, or are they using this convention to give you the primitive vectors? Okay. Let me now discuss an additional Bravais lattice, very common one in 3 dimensions. In fact, this is now probably the most common Bravais lattice in 3 dimensions. And it's the one taken by aluminum, in fact. This is the face-centered cubic lattice. Face-centered cubic, or FCC. How does it look like? Still, we start with a cube. You place your points here at the edges of the cube. But in addition to these points, of course, again, you have to repeat everything to plus and minus infinity. In addition to these points, you place points in the center of the faces of the cube. You put 1, you put 1, you put 1 in the back here, you put 1 here, and you put 1 here in the front. Okay, so you place additional points, which means that if I have another cell here, I need to continue this, and I need to place atoms everywhere, right? Also here in the back. Now things are getting a bit more complicated here, right? Once again, I can discuss this, I can describe this as a crystal structure made of a simple cubic Bravais lattice. The primitive vectors are the simple cubic primitive vectors, A1, A2, and A3, right? Plus now 4 vectors in the basis, B1, B2, B3, and B4. B1, of course, is 0, because this point is there, belongs to the lattice. And then with B2, I have to reach all the points at the centers of the faces. So B1, B2, and B3. Well, sorry, you're right. 2, 3, and 4. Thank you. But wait a sec. I added more points here. What about this one? Should I introduce a B5, a B6, a B7? Why? Very good. So I don't need to introduce a B5 here because this point can be reached through B4 by adding A1. Okay, so all the other points can be reached by linear combinations of integer times my primitive vectors plus one of the 4 basis vectors. Now it can be shown, it takes a while unfortunately, but it can be shown that this can be described also as a Bravais lattice. The FCC can be described with a Bravais lattice. And I'm not going to show it, although, I mean, I can show it now briefly, but it's not going to be very clear. But the 3 primitive vectors are going to be B2, B3, and B4. In other words, one can show, don't ask me to do it here because it's a bit complicated, that if I take integer times B2 or B3 or B4, I reach all the points of the FCC lattice. It's not going to be easy, by the way. Suppose I want to reach, for example, suppose I want to reach, let me do a simple example. This one, here. Suppose I want to reach this point. Can anybody tell me how I can reach this point using B2, B3, and B4? Can you see that? So, sorry? 2 times B4. If I go 2 times B4, I end up here. B2. So you're suggesting to do B2, then B3, I'm going here. And then? B3 first, and then? Once more B3 and end up here, because I'm at the center of the face, so I go here. Come on. let's start B4. Let me climb here. I'm in the middle of the face here. I need to get to this point, and that's in the middle of the face there. So what do I need? From B4 to get to here. B3, right? So this point is B4 plus B3. Okay? Don't ask me to do the other ones. Trust me. You can reach all the points of this lattice by... in fact, it's enough for me to show you that you can reach the primitive vectors as well as... and that's it, sorry. It's enough for me to show that with these 3 vectors, I can reach the 3 primitive vectors. Once this is done, I can say, okay, I've been able to generate my Bravais lattice, and then all these points are already there. So it's enough for me. It would be enough for me to show the equivalency to show that with these vectors I can generate the 3 primitive vectors of the simple cubic cell. It can be shown. I mean, it takes a while to show it. Anyway, the bottom line is that the FCC lattice can be described either as a crystal structure made of a simple cubic Bravais lattice plus 4 points in the basis, or as a Bravais lattice with primitive vectors defined by B2, B3, and B4. Okay? Once again, it is clearly much simpler to visualize the structure and to have a feeling of what the structure looks like if you look at it from this perspective than if you look at it with this perspective. So you're simplifying your life because you have only one element you have a Bravais lattice, which is much simpler, geometrically speaking, but of course, you lose a lot of simplicity in the way you visualize the structure by doing this. The important point, however, is to remember that the FCC is also a Bravais lattice, or can be described by a Bravais lattice if you wished. All right. The FCC lattice has another very important property, but you won't be able to see it if we discuss the lattice in the way we've discussed it now. So let's discuss now at first glance, something that looks completely different, which is how to better, more efficiently pack spheres in space. So now we're going to study the packing of spheres in 3 dimensions. This is an interesting geometrical concept because atoms, after all, they are spherical objects, particularly metal atoms. So, and of course, we know that atoms like each other. So the hypothesis is that if we draw a number of atoms and we try to see what is the best way in which they can pack, the best way in which they can pack will resemble the way spheres pack in space. All right? So we've already discussed the packing of spheres in 2 dimensions. Right? We've already seen that in 2 dimensions, spheres like to pack in a triangular lattice. You remember this, right? We had this drawing here. And we realized that this is, in fact, a triangular lattice that generates, in principle, the whole system. So if we reduced all these spheres to a point, these points would lie on a triangular lattice. And that's the best way to pack spheres. By the way, what do I mean by best way to pack spheres? Of course, I mean the way in which I minimize the empty space. But I'll come back to that in a moment. Okay? For the time being, let's just, I guess it's clear to everyone that this is the best way to pack spherical objects or circular objects in 2 dimensions, right? There's no better way to do that. Let me now extend my considerations to 3 dimensions now. So the way we're going to do it is a very, practical one. We're going to imagine to have balls, spheres, soccer balls, and we're going to throw them try to fill this room with balls and try to do it in a way that optimizes the packing of these balls. So the first thing we do, we just throw the balls on the floor, and we're going to find that the balls pack in this triangular fashion, right? Suppose we fill the whole floor with balls, and they're going to, of course, and try to pack them as much as possible. They will take this pattern on the floor. And now we're going to draw a second layer of balls on top of this one, right? Of course, the second layer of balls will also try to pack in a triangular way, in a triangular fashion. But in addition to that, the balls will try to to sit in those places where there is an empty space here, right? Because this is where they can actually optimize their height. They certainly are not going to pile up on top of the other ball. They're going to end up in this hollow site here. Okay? So let me now assume that perhaps the first one ends up here. The second one will fill this one here. The third one will end up here. The fourth one here, and so on and so forth. Right? So we have, let me actually shade them a little bit so that you can recognize them. And I can build a second layer of triangular balls that lies perfectly on top of the first one. Let me actually highlight the centers here, because the centers of these balls, as you clearly see, they are going to be filling the hollow, the dips in the corrugation of the first layer. Notice, however, that I could have done it in a different way. I could have placed the first ball at the center of this dip, right? And then the balls would have arranged here, 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 and so on and so forth. You probably noticed that here you have a triangle pointing upwards, and here you have a triangle pointing downwards. So they're clearly different. So I can either place the second layer of balls where the triangles point up, all up, or I can place them in all places where the triangles point down. So I have two possible ways to construct the second layer of balls, either on top of the up triangles or on top of the down triangles. So let me call the first layer A. The second layer, I'm going to call it B. But I want to keep in mind that I could have chosen another location, which was the triangles down, which I call C, and I just keep it here just to remember that I could have placed the atoms here, the balls here, right? And just mark the points here just for me to remember where they are. But I could have placed the balls in the green point sites, and I call this the C configuration, which I'm not using here. Fine. Let me now draw the third layer of balls on top of the layer B. Again, I will have two possibilities. I will have the possibility where the third layer, I'm not going to draw it because otherwise it's going to be a mess, okay? But I will have the possibility to start with an upper triangle for the pink, for the B layer, or with a downward triangle for the B layer, okay? Now notice that the upper triangle for the B layer coincides with the green point. You can see it, upper triangle here. Here you go. It is exactly on top of what used to be the down triangle before. So my choice, one of the two choices for the third layer is indeed C, in terms of where it stands relative to the two-dimensional layer. The second option is to place my atoms on top of the down-looking triangle of the pink layer, here. Here, here, where is it? Here, here, and so on and so forth. But this one is exactly the center of the original layer, A. Okay? So for the third layer, I have two choices, either C or A again. Right? So I've done A, I've done B, and then the third layer can either be A or C. Now it's quite clear that if I keep continuing with that, I can either place the atoms layer by layer in A, B, or C positions. I only have three choices. And each time I draw the next layer of balls, if the previous one was a B, I can only choose A and C. I cannot choose B, of course, because otherwise I would fall on top of the previous one. If it was A, my choice would be B or C. If it was C, my choice would be A and B. Okay? And these are all equally good in terms of packing of spheres. Okay? That is, I can choose any arbitrary sequence of A, B, C, B, whatever I want. I mean, C, as long as I every time change my color, is going to give me a very efficient packing of spheres. And I can identify my sphere packing by just giving a sequence of 3 letters or 3 colors or 3 something. The only thing I have to be careful of is that there is never a repetition between nearest neighbors. Okay? Every time I move, I have to change it. It must be different. But any sequence is fine in principle. Now, it takes a while to visualize it, and we're not going to do it because it really requires some sort of three-dimensional vision to realize this. But FCC, the FCC structure, is equivalent to ABC, 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 repeated periodically. Okay? So this is really an equivalence, the same thing. The FCC structure can also be seen as a sequence of triangular layers packed in this fashion, A, B, C, A, B, C, A, B, C. So with a threefold periodicity. There are other structures that are well known in nature, like the hexagonal close-packed structure, which is characterized, it's even simpler. It's AB, AB, AB. And they exist in nature. Aluminum, for example, crystallizes in the FCC structure. Titanium, for example, crystallizes in the HCP structure. Or iron at high pressures. I mean, there are several elements that crystallize in the HCP structure. They're all equally good in terms of sphere packing. But they just differ in the way these layers are stacked on top of one another. I may even have disordered sequences of layers. There are systems, particularly if you go to high temperature, in which the ordering of the layers becomes lost, and therefore you have an arbitrary sequence of layers in a random sequence of layers, ABC, ABC, ABC. All right. I promised I would go back at some point to what I mean by packing. What is the meaning of most efficient packing? Okay, we know what we mean. We know that we mean minimizing the empty space. But we need to be a little bit more precise when we say this. So before I get to the concept of packing fraction, which is exactly what we have in mind, the fraction of empty space with respect to the whole space available, I need to introduce another important concept in the theory of lattices. Because so far we've been talking about just points. While as soon as we start talking about volumes, space, we need to find a way to measure that space and to identify what we mean by space. So far we've only introduced the discrete points. At least our mathematical objects were made of discrete points. So let me go back to the very simple example just to visualize what I'm going to talk about now. So this is our good old square lattice with our primitive vectors A1 and A2. And let me introduce now the concept of unit cell. What is a unit cell? Well, let me first draw it and then we'll define it, okay? So for this particular lattice, a good choice of the unit cell could be this square. What do I mean by that? I mean that if I take this square here and I translate it by any of the primitive vectors, by translated by any Bravais lattice point, that is any multiple integer of the primitive vectors. For example, if I add to this square A1, I'm going to translate my unit cell here. If I translate it by A2, I'm going to fill this region. If I translate it by A1 plus A2, I'm going to fill this region. Now, the beauty of this choice here, which is rather natural, is that by translating this green area by any Bravais lattice vector, I'm going to fill the whole space. And I'm going to fill it in a very clever way because I'm going to leave no empty space. And in addition, these unit cells, these objects, are not going to overlap with one another. Well, of course, with the exception of a region of zero measure, which is just the edge of the square. But we are physicists, we are not mathematicians, right? So we don't worry about regions of zero measure. So the beauty of this green area here is that if I translate it by all possible values of the Bravais lattice points, I cover the full space without overlaps and without leaving empty spaces. Okay? So this is exactly what I mean by unit cell. It's the region of space of course, here it is in 2 dimensions, but in 3 dimensions it will be a 3-dimensional region of space, such that if translated by all Bravais lattice vectors, it covers the whole space no overlaps. Okay? Think of it as a way of placing tiles on your Bravais lattice. You want to choose a tile that, if repeated with the Bravais lattice vectors, covers the whole space and doesn't leave any empty space. Obvious questions. Would this be a good choice for the unit cell or not? Yes or not? No. If I translate this octagon by a Bravais lattice, I'm certainly going to have some overlaps here, for example. And I'm not going to fill the whole space because this region here is going to be left empty if I translate this octagon with all the possible Bravais lattices. Notice I have to translate it with all the Bravais lattice points, not with other points. Okay, so this octagon is not a good choice of the unit cell. Let me take another one now, this one. Is this green area a good choice for the unit cell? I'm afraid yes. I translate it by this, and I'm going to do this, right? I translated using A2, and I'm going to end up here. I translated by A1 plus A2, and I'm going to do this. So this is a good choice of the unit cell. In general, good choices of the unit cell, legitimate choices of the unit cells, are regions of space characterized by this property in 2 dimensions at least. S1A1 plus S2A3, where S1 and S2 are between 0 and 1. In 2 dimensions. In 3 dimensions, of course, this. Oh, sorry, A2 here. What kind of region am I describing with this? Is this clear to everyone? Suppose I have A1 and A2. What is the region of point that I'm describing with this vector R defined as fraction S1 between 0 and 1 of A1 and fraction between 0 and 1 of A2? So A1, I have to take all possible values between 0 and A1, because S1 ranges from 0 to 1, and S2 can take any value between 0 to 1, so I'm taking all possible values of the vector from here to here. So when I take the sum of the two, I'm defining the whole region, right? Is this clear to everyone? Say, let me take this point, for example. This point would be characterized by, roughly, 0.8 times A1 plus, whatever, 0.3 times A2, right? So you see there are fractions of A1, a fraction of A1 in this direction and a fraction of A2 in the other direction. If I take all the points here, they will be characterized by fractions between 0 and 1 of A2 or A3, or A2, A1 and A2, sorry. Okay? So this region of space with S1 and S2 going from 0 to 1, not together, of course, right? Independent from one another. So S1 is not necessarily equal to S2. They can take any value between 0 and 1, both. I'm covering the whole space identified by these two vectors. If S1 and S2 are both 1, I will end up here, right? It's A1 plus A2. By the way, if A1 and A2 are not orthogonal, A1, then what I'm identifying is this region, right? It's the region where made of the sum of fractions of A1 and A2. At most, it can be A1 plus A2, which is this point. All the other points are fractions less than 1 of the two vectors. So, if you give me the primitive vectors, I can tell you for sure that this is a good choice of the unit cell. And because there are infinite ways, infinite possible choices of the primitive vectors, there are also infinitely many choices, possible choices of the unit cell. The green one, the square one, is equivalent to the, is equally good as the pink one. And you can immediately recognize that the green one was this choice with A1 and A2 being the two, standard vectors for the square lattice. And the pink one was the same choice but with A1 and A2 being the primitive vectors of the square lattice, which is an equally good choice for the primitive vectors of the square lattice.
A question.
Yep.
Okay, the unit cell must it lie within the points? Like
The unit cell, no, okay, good point. Your question is whether the unit cell must lie between points of the Bravais lattice. The answer is no. Let me take, in fact, that was my next example. Let me consider now this choice of the unit cell. Okay, so this area here, this square. Is this a good choice of the unit cell or not? Yes, it is, because I translate this cell by a lattice, by a Bravais lattice point, and I end up here, and so on and so forth, right? This choice is a bit different, because I'm placing the Bravais lattice point right at the center. In that notation, by the way, it would be equivalent to saying that S1 and S2 go from minus 1/2 to 1/2. Okay, that's equally good. Because if this is the origin, this is A1 and this is A2, the two primitive vectors, this pink square here identifies all the points that can be written in this form with S1 and S2 going from minus 1/2 to plus 1/2. Right? So this is equally good. There are plenty of choices. I mean, there are, in fact, infinitely many possible choices for the unit cell. Yeah. Yes? Are what? Greater than, so the question is, what happens if S1 and S2 are greater than 1? What do you mean by that? I mean, this is the definition of the unit cell that I give you. You want to know what happens if S1 and S2 are greater than 1, right? You're constructing a vector which goes beyond, if A1 and A2 are here, if S1 is greater than 1, then you're staying somewhere here, right? Outside this line. I mean, you may wish to, I mean, you can also construct, you can take this one as the unit cell. Okay? This is also good because you can translate this and you would obtain the whole system. Now, that cell would be characterized by 1, right? 2. Right? If you take this one as the unit cell, these points, for example, would be characterized by something between 1 and 2 times A1, right? And that's equally good. So S1 and S2 can be larger than 1 if you wish. Of course, you have to make sure that you limit your choice of S1 and S2 to, well, to a range of length 1, essentially. If it's more than 1, then you're going to have overlaps. If it's less than 1, you're going to have empty spaces, right? In fact, in principle, it can be any choice, right? It can be any constant and constant plus 1, right? You would just be translated your unit cell, but if you translate the unit cell, you're not losing these properties in no way. Okay. Let me continue with other possible choices of the unit cell. Now it will take me a little bit, right, to draw it. Let me do this. I'm of course exaggerating a little bit, but is this a good choice for the unit cell or not? Is it or not? It is, right? So it's a very exotic one, but it is a good choice because I take this tile here and I translate it by my Bravais lattice points, and I'm going to fill the whole space, and I leave no empty space, and I'm not going to overlap anywhere. Okay? I will never choose such a unit cell, by the way, in real life. But that's to show you that the choice is in principle arbitrary, and you can make it as complex as you wish, in principle, if it is more convenient for your studies, for your research. So this is, yes, this is a good unit cell, in principle. By the way, I cannot write the points inside the unit cell in the compact form that I gave you before. So I won't be able to write the set of points that are enclosed in this green area like S1 times A1 plus S2 plus A2, right? Because I need to, the borders, the edges of these tiles are very complicated. So I just need to, I can only visualize it like this. I cannot give you a detailed prescription on how to express this region here. Yes?
Can we do this? I think it would be easy, like if we take a sphere, and then if we cover the sphere with this lattice, and then we will have a circle, right?
Yes.
In principle?
So wait a sec, let me repeat it. So you want to have a sphere?
No. Okay, just to make it easy, to
Yes.
feel like this thing, we take a sphere, and then we cover the sphere with this.
We cover the sphere with this unit cell?
No, the whole lattice.
We cover the sphere with the whole lattice? What do you mean by that?
Okay, we have a mapping called conformal mapping, right?
I think you're heading too far, from here. Okay, go ahead, yes.
Yeah, because all are in fact the same. If we cover the sphere, they represent a circle on the sphere.
Okay, I think you're getting back to this idea of boundary conditions that we're going to analyze a bit better in the future, in a few lectures from now. For the time being, I don't think the concept of boundary conditions is so relevant for our discussion when we talk about unit cells and so on. But it will be relevant, very relevant in a few lectures. Okay? So the idea that somehow it's easier to see an infinite system by assuming that at some point there is some sort of boundary conditions that close, that make the something, finite.
If we project the plane onto a sphere, it's okay. It's just a sphere, the whole plane.
Right.
So this is an infinite plane.
Yes.
And if we project it on the sphere,
Yes.
and then those lines represent a circle on the sphere, and all those things are in fact the same.
I'm afraid that they're not going to gain too much if you do this mapping. I might be wrong, but I'm afraid it's not really going to be of help unless, you want to discuss concepts like periodic boundary conditions. But again, we'll come back to that later on. Okay. Yes. The last thing I wanted to say about unit cells is this. Well, actually, there are two things I wanted to say. The first one is something perhaps obvious, but I think it's worth discussing it just for the sake of clarity at least. Let me use, the simpler example of a square lattice as usual. And let me take an arbitrary point in space, say this one. Let me call it R. Okay? It's an arbitrary point in space. It's not a Bravais lattice point. It's a point in space. Now, if these are my two primitive vectors, Because they are independent vectors, I will be able to express R as a linear combination of the two vectors, right? So I will use R1, A1 plus R2, A2. R1 and R2 will be arbitrary numbers, real numbers. Any point in space, I will be able to describe it in this way. Obviously, if my point coincides with a Bravais lattice point, R1 and R2 will be integers, right? If R1 happen to be inside this square, what would be the property that characterizes R1 and R2? They will be both less than 1, between 0 and 1. But because I chose an arbitrary point, R1 and R2 are arbitrary numbers. However, I'm still allowed to say that if I chose, for example, this one as the unit cell, I can say that R belongs to this translation of the unit cell I have chosen at the beginning. What do I mean in practice in terms of this way of expressing the position, in terms of linear combination of the two primitive vectors? Well, what I've just said is that points inside this area are characterized by this expression where S1 and S2 are less than 1. But this point belongs to the next unit cell, that is to a unit cell which has been translated by A1. But then what I'm saying is equivalent to say that this R1 can be decomposed into an N1 plus S1, A1, plus, in principle, an N2 plus S2, A2. That is, any real number, I can express it as the closest integer plus a number which is between 0 and 1. Same with R2. Any integer number, I can express it with the closest integer, I mean, on the left side, let's say, and a number S that is between 0 and 1. So what I'm saying is exactly what I just said before, namely, if I group N1 and N2, this is a Bravais lattice point. And then what I'm left with is S1, A1 plus S2, A2, which is a vector in the unit cell, because S1 and S2 are less than 1. Okay? I just wanted to show you that if you use this notation, you can immediately, recover the discussion that we just made before, namely, that for this to be a good unit cell, this is obviously, a simple way to see what I'm doing in space. I'm using unit cells to cover the whole space, and if I write it down mathematically, what I'm doing is simply to decompose these numbers, these real numbers, into integers and whatever remains. Integer part will be my Bravais lattice, the Bravais lattice through which I have to translate my unit cell, and the rest will be the position of the atom in the original unit cell. Okay? Sorry, in the original cell, in the translated unit cell here. Okay? So this part here will be, so it would be like writing this point as a linear combination of R plus this vector, let me call it S, a vector which is within the unit cell. Yes, and any point in space, I will be able to write it as a linear combination between a Bravais lattice point. I simply need to go to the closest Bravais lattice point and then move with the unit cell vector inside the cell. There was a question? You were...
So, when you are doing that, I think it's like you have R2, because I can't translate, it's R2 and not this none, another part.
Here.
Not this one.
Oh, here, sorry.
No, okay. This, when you want this, I call R1 transfer to R2.
Right.
In the end of you find this. This means like I have R2.
block.
This one.
No, this one. I want to know because I copy
R2, let me repeat it, okay, so that it's clear. Let me actually repeat it in the opposite way. Let me do the argument the other way. I just said that the unit cell cover the whole space if translated by an appropriate Bravais lattice vector. So if I have a point that belongs to a unit cell translated, okay, and it must belong to a translated unit cell because the assumption of the unit cell is that if I translate it, I cover the whole space. So wherever I am, I will find a Bravais lattice vector that brings me the unit cell close to where I am. So I'm here, and I can therefore say that if I want to reach this point, I can do it by summing a Bravais lattice point plus a vector inside the unit cell, which is what I'm writing here. I just wanted to show you that this could be easily seen also mathematically by saying that the same point can be written as an arbitrary number, real number, times the primitive vectors, because primitive vectors are independent vectors, and therefore I can construct any point in space as a linear combination of these two vectors, real numbers. But any real number can be decomposed into an integer plus into the closest integer to the left, plus a number that is between 0 and 1. And if I do that, I clearly extract out the Bravais lattice vector and the vector in the unit cell, S. Okay? If I had a point, say, I don't know, here, for example, then my R would have been this one, and then S would have been this one. Okay? So wherever I am, I can go from the origin to where I am by first reaching the Bravais lattice point and then moving inside the unit cell. Which brings me to another important concept, which is that of the Wigner-Seitz unit cell. Eugene Wigner and Friedrich Seitz were two of the pioneers of solid-state physics in the 30s and 40s, and they came out with this. Yes. In the first case, which one? Here? Yeah. It looks like we put what? Yes, correct. Yes. Here, there would be here, n1 would be equals to 1, and n2 will be equals to 0. Yeah, correct. Hmm? Here, yes, that would be 2 minus 1, yes, and 1, and then a small vector inside the unit cell. Now, that brings me to the concept of Wigner-Seitz unit cell. It's yet another definition of the unit cell. And what does it say? Well, I choose as a unit cell the set of all vectors for which the origin is the closest Bravais lattice point. Okay? So the set of points for which the origin, of course, understood as the r equals to 0 Bravais lattice point, n1, n2, n3 equals to 0, is the closest Bravais lattice point. In this plot here, what would be the Wigner-Seitz choice of the unit cell? Here. This is the origin. What is the set of points for which this is the closest Bravais lattice point? Well, certainly, if I move around the origin, of course, these points will have this one as the closest one, right? But what are the other ones? Well, I have points here. I have point here, 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 here. Well, so clearly, this square here is the set of points for which the origin is the closest Bravais lattice point, right? If I had chosen a point here, there would be this one. This point would be closer to this Bravais lattice point. If I go here, well, it's closer to this one. If I go here, it's closer to this one. In fact, these are the lines that, divide the segment in two, right? It's perpendicular to the segment. Same with this, same with this, same with this. If I do the same trick with this, the perpendicular would be here, so there would be no gain in that, right? So this square here is clearly the region of space for which the central point is the closest Bravais lattice point. In fact, if I now think it in these terms, it's even more natural. How can I assign an arbitrary point to a unit cell and to a Bravais lattice? Well, I just look for the closest Bravais lattice point. And then I have to, so this point, for example, using this choice of the unit cell, would be described by this that brings me to the closest Bravais lattice point, and then by this vector here. So I would still reach the same point, but I would reach it in a different way, because the choice of the unit cell is different. It's not this one. I've chosen a different definition of the unit cell. Okay? And in some sense, it is more natural, because I'm not introducing primitive vectors, for example. Notice, this is very important. This choice does not depend on choice of primitive vectors. It's unique. I don't need to specify anything else than the Bravais lattice to identify the Wigner size unit cell. And it's also somehow natural from a geometrical point of view, right? Because any point in space you want can be identified through its closest Bravais lattice point. It's like thinking at the fastest way to get to an arbitrary place in a country, right? You first go to the closest town, and then from the town you go to the village. If you want to minimize the time it takes to get to any point in your country. So that's a spirit. Sorry?
Please repeat the explanation again.
Okay, so this is the definition. And I've now applied this definition to this example using my R point here. Now, because the unit cell is defined as the set of points for which the origin is the closest Bravais lattice point, here in this definition, the unit cell would be this square, which is what we just discussed on this side here. So if I translate it, it will end up here. What does it mean? That this point is the closest point, Bravais lattice point, to this one. So if I take an arbitrary point in space, and I want to assign the corresponding Bravais lattice point to which it belongs, I simply have to look for the closest Bravais lattice point. Okay? So I subdivide my space. This definition of the Wigner size unit cell, it's such that I subdivide my space in such a way that every region of space has the Bravais lattice that is contained in that region as the closest Bravais lattice point. Okay? It's like subdividing a country in such a way that every village has a town as a closest place, the closest town. Okay? And here, of course, we are doing it for a regular lattice, so it's geometrically more regular. And the beauty of this definition is that this does not depend on the choice of the primitive vectors. Nowhere here I specify even about the existence of the primitive vectors. I don't know what I don't need to know what the primitive vectors are. There is a unique choice independent of what the primitive vectors are. Yes?
In this case, R is
R, capital R, you mean? No, in this case, no, capital R would be this one, right? I have to go to the closest Bravais lattice point. So capital R will be this one. All right. So that's the unit cell. Remember, the unit cell is something that if I translate it, I cover the whole space. Okay? So this is my unit cell. In order to cover the whole space, I have to translate it. So in order to cover this point, I need to translate it up to this point using capital R, this Bravais-Lattice vector. So in other words, if I want to express the position of this point, I can do it by first taking this Bravais-Lattice vector, and then taking a vector within the unit cell. All right? So the concept of, this unit cell is something that I define at the origin. But then in order to find an arbitrary point, I need to translate this unit cell with the Bravais-Lattice vector. So what I'm saying here is that this small r can be obtained by translating the unit cell up to here, and I have to use a Bravais-Lattice vector to do that. Plus, I can move inside my unit cell with a short vector, r. Okay?
So, but in this point, R cannot be equal to 0.
Sorry?
The image of yes, in this point, no. Yes, R cannot be equal to 0 if you want to find.
Cannot what? Sorry, B?
Big R cannot be equal to 0.
No, of course. R will be this one, yes. But, remember, it's the regional space that, if translated, covers the whole space. Okay, so I have to translate that regional space to obtain the whole space. Right? So first, I define it here at the origin, and then I need to translate it in order to cover the whole space. So if I take an arbitrary point, I need to tell you two things. I need to tell you how I need to translate my unit cell to the closest Bravais-Lattice point, and then how, within the unit cell, I go from the Bravais-Lattice point to my specific point. Okay, I need two pieces of information to reach an arbitrary point. The Bravais-Lattice vector and the small vector inside the unit cell. Yeah.
Why need this unit cell very important and crucial? Why we need this extra definition?
You mean this definition here?
Yeah.
Or
When this is important and crucial?
when is this definition? When is the definition of the Wigner size unit cell crucial?
When is applicable? We have to use this thing.
Well, you can in principle use whichever you like. Okay, depending on the kind of problem you want to solve. I'm simply arguing that if I tell you construct the Wigner size cell of the square lattice, you'll be able to construct it without me telling you what the primitive vectors are, okay? Because it's a geometrical property. It's intrinsic of the lattice. We know that every Bravais lattice can be expressed in an with infinitely many different possible choices of the primitive vectors. All the choices we discussed before, these ones, for example, required me to give you A1 and A2 in order to define the unit cell. This one does not require me to tell you anything. So you can come out with a unit cell just by knowing what the Bravais lattice is, without defining what the primitive vectors are.
It's just another choice.
It's another choice, yes. I'm simply arguing that this is more natural. Okay? So there are examples in which you should be using this one.
Do we have another extra definition besides this?
Well, I think we've covered essentially the simplest ones, at least. Yes?
In the case of the crystal structures,
Yes?
to define the unit cell, do we need just the Bravais lattice?
Okay, so your question is, in the case of a crystal structure, the definition of the unit cell relies on the Bravais lattice or on the crystal structure in general? The first one. In the case of a crystal structure, the unit cell is defined by the Bravais lattice that defines the crystal structure. Okay? What this implies is that in each unit cell, there will be more than one point. In fact, there will be as many points as the number of basis vectors. Okay? So inside the unit cell, there will have to be a number of points equal to the number of basis vectors. Okay? Good. Very good point. Thank you. Just to make another example of Wigner-Seitz unit cell. Let's take the triangular lattice. Again. Okay, so we have a triangular lattice. These are the primitive vectors. But in principle, I don't need to tell you what the primitive vectors are. But I want to know from you what is the Wigner-Seitz cell of this lattice. The origin is here. So we want to find out the region of space that translated covers the whole system, but for which the set of points, we want to find the set of points for which this one, which is the origin, is the closest point. So what do? Well, we draw lines connecting all the possible nearest points. Well, and so on and so forth, of course. There will be... and then we construct the perpendicular, right? Because we can be sure that points to the left of this line will be closer to this one than to this one, right? Same with this. Same with this. Same with this. Same with this. Wasn't so nice. What comes out, trust me, is a perfect hexagon. You probably knew that, right? That if you take an hexagon, you can fill the space with a triangular lattice. If you try to fill the space with hexagons, you will generate a triangular lattice. So this hexagon here is the Wigner-Seitz cell, unit cell for the triangular lattice. Bravais lattice. Okay? So this is just to warn you that the Wigner-Seitz cell might take a shape which is perhaps not easy to predict based on the, while for the square lattice it was trivial, right, to identify, or very simple to identify the square as the Wigner-Seitz cell. For a triangular lattice, this choice, the shape of the unit cell, of the Wigner-Seitz unit cell is less obvious. By the way, we can compare it with the choice based, for example, on A1 and A2, right? The one S1, A1, S2, A2, and this one would look like this. So the pink choice would be the choice of the unit cell according to the primitive vectors A1 and A2, and the green one is the choice of the unit cell based on the Wigner-Seitz criterion. And you clearly see that they're quite different. Yet, both of them, if translated, cover the whole space without overlaps, without empty spaces. But they look quite different, admittedly. Now, an interesting property, and now you see it in the triangular lattice of the Wigner-Seitz cell, is that it preserves the symmetry of the Bravais lattice. The triangular Bravais lattice has this 60-degree symmetry, right? If you rotate it by 60 degrees, it goes into itself. Now, unfortunately, the pink choice, if you rotate it by 60 degrees, it doesn't go into itself. It goes into another unit cell, equally good choice of the unit cell, but it doesn't go into itself. The green choice, Wigner-Seitz, goes into itself. So this is another interesting property that the Wigner-Seitz cell has. not only does not depend on the choice of the primitive vector, but it preserves the symmetry of the Bravais lattice. Okay? Which the pink choice does not. Okay? The pink choice does not preserve the symmetry. You rotate it by 60 degrees and you obtain something else. It's equally good, equally valid, but unfortunately it does not preserve the symmetry of the Bravais lattice. Okay. I think we can probably stop here. Is there any further question? Yes. Mm-hmm. The pink choice, okay. You want to discuss the pink choice of the unit cell, yes. No, it's not the same. I mean, you might be erroneously think that they're the same, but they're not. I mean, this one, you see this point is on top of this one. This is 60 degrees. This is an equilateral triangle, so they're not the same. The Wigner-Seitz cell here, yes, it is a square, yes. Here, the Wigner-Seitz cell is a square. Unfortunately, or fortunately, also the unit cell generated by the two primitive vectors is a square. So in this particular case, even the other choice, the primitive vector choice of the unit cell, works, preserve the symmetry. But here it does not. While the Wigner-Seitz cell always preserves the symmetry of the Bravais lattice. Any more questions? Yes?
Is it always possible to construct unit cells for any kind of crystal structure?
Well, okay. So the question is whether it's possible to construct unit cells for any kind of crystal structure. The answer is, well, first of all, the unit cell for a crystal structure is the unit cell of the Bravais lattice, the underlying Bravais lattice. So the question can be translated into can we construct a unit cell for any Bravais lattice? Right? Because what we define as unit cell in a crystal structure is the unit cell of the, as we discussed a minute ago, is the unit cell of the underlying Bravais lattice. So the question is, can we construct a unit cell for all possible Bravais lattices? The answer is yes. Take this definition. It does not depend on the Bravais lattice, so you can apply this definition to any Bravais lattice. And that will give you a legitimate choice for the Wigner-Seitz cell, for the unit cell. So every Bravais lattice, that means every crystal structure, will have a unit cell. You just need to follow this prescription, and that gives you the way how to construct it.
If these unit cells do not contain the basis vectors, then why are we interested?
Okay, that's a very good point. So let me just digress 1 minute because this question of the crystal structure, I guess, is something you are interested in. So let me... so you are somehow, I guess, if I understand correctly, you are worried that suppose, let me make an example to clarify what I tried to say. So we're still talking about the square lattice. And then we have, say, a lattice with a basis, a crystal structure, composed of the square Bravais lattice plus 2 points, one here and one here. So B1 and B2. Okay, so this is A1 and this is A. I'm trying to rephrase this with an example. Then you say, okay, now let me construct the Wigner-Seitz cell. Wigner-Seitz cell, this is the origin. But wait a second, my points are outside the unit cell. Is this what you are trying to get to? Fine. So my points are outside the unit cell. What do I do with that? Well, there are many things that I can do. First of all, there's nothing wrong in saying that there are 2 points outside the unit cell, because if this is outside the unit cell, there will be his friend here coming from the other unit cell, right, which will be located here. So by translating this, I will find a translation that brings me B2 inside the unit cell, right? So if it was initially outside, fine. By translating it, since this is just one element in the basis, but I have to translate, in order to obtain the full crystal, I have to translate this by all possible Bravais lattice vectors, there will be certainly one and only one friend of B2 that falls inside the unit cell. So then let me choose this one instead of this point for simplicity. Okay? So I don't really need to or, I mean, the other possibility is to say, well, I don't choose the Wigner site cell, but I choose this one. Then I'm fine. My B1 and B2 will be inside. Okay? So this is why there is, I mean, one can exploit that freedom, the freedom that we have in generating the unit cells, depending on the problem we want to solve. Here, I mean, you have two possibilities. Either constructing the proper unit cell in order that B1 and B2 are included, or if you want to choose the Wigner site cell, you just have to consider that you have to translate B2 by one Bravais lattice vector, and there will be a point inside the unit cell that is equivalent to B2.
Can we also change the base?
Yes, at that point, why not? I mean, of course, if I have B1, an element in the basis, I can always decide to take another one, to change it by taking an arbitrary Bravais lattice vector, obviously, yes. Of course. If I take an element in the basis and translate it by a Bravais lattice vector, it's the same, right? Because I will always have to translate this by all possible Bravais lattice vectors. So if I can translate it at the beginning, and who cares? So yes, I can do this. Yes. I have to be careful not to consider both, however, right? I have to be careful because if I take this and this, then I will be wrong, right? Because this is the same translated by a Bravais lattice vector. So I cannot put both in the basis.
Can we define the basis as all the possible vectors who reach a point inside the cell?
Okay, yes, yes. I mean, yes. If you wish, once you define your unit cell, you can say, okay, let me force all the elements in the basis to be within the unit cell. Yes, you can do that. You're allowed to do that, but if your friend does not want to do it, you cannot forbid her not to do it, of course. Okay? More questions? Okay, fine. So see you on Monday.